Okay.
Right?
No,
bachelor's.
bachelor's.
Okay.
Have a ticket.
Yeah, I do.
Okay. I guess we are ready. Hello, everyone. We are starting today with the presentations. Topic is about talking about DRAM and how we do integration in DRAM. And then in the next presentation, we'll discuss about the disturbance phenomenon. So let's start with the first presenter.
So this is Christopher Rumenap. He's a second-year computer science bachelor student, and his main interests are computer architecture, digital design on FPGAs, and low-level systems. So, Christopher?
Can I start?
Yeah.
Hello, I'm Christopher, and I'll be presenting self-managing DRAM, a low-cost framework for enabling autonomous and efficient in-DRAM operations. It was presented at Micro 24. Now I'll start off with an executive summary. DRAM reliability demands frequent maintenance operations, such as row refresh, RowHammer, and memory scrubbing. However, introducing and improving these operations currently is a very lengthy process, as it requires changes to the DRAM interface, which takes a whole process with JDEC. Now, the goal of the paper is to ease and accelerate implementation of new in-DRAM maintenance mechanisms and to enable more efficient and flexible in-DRAM maintenance operations. Now, the key mechanism we're working with here is that the paper introduces a single and simple DRAM interface modification, which will let DRAM autonomously manage and schedule internal maintenance. With SMD, DRAM will be able to reject accesses by the controller to actively maintain regions, which will allow concurrent access to the other regions in the DRAM as well. This will allow future maintenance operations without any further changes to the DRAM interface. The results we're seeing with this paper are an average speedup of up to 5%. And there will be minimal overhead on the chip itself. New maintenance operations can also be introduced without any changes to the DRAM interface.
Sorry to interrupt you. There's something wrong with Zoom.
Okay.
So before you continue, I'll try to fix it. I just want to get PPT. Why is your PPT? Or is it something else?
Oh no, I'm using Keynotes.
This is it.
Yeah, it's open number as well.
Which one is it?
The blue one. No, this app.
Okay. Okay, so this is presentation mode.
No, presentation mode is on the play.
And you don't want that.
Oh no, I do want. I
Okay.
do want this. Yeah, it would be this screen.
Sardina, you should come here. Ah, that's it.
Yeah.
That's it. Uh-huh. Then go first. This is what you did.
Yes.
And still nothing. See now? Yes, I can see correct.
Does it change when you animate?
What?
Yes. Doesn't show on Zoom.
Okay.
So I think it's okay.
I cannot see where
Yeah,
the
yeah.
mouse is
It's okay.
because of
It's not visible on Zoom.
Keynote doesn't allow the mouse to move.
Well, there's nothing up there anyways, so it shouldn't really present any issues. Okay, so I'll be continuing by giving a little more motivation about why this is necessary or useful. The current DRAM interface has the memory controller send DRAM commands to the chip or to the DRAM chip. Those are memory accesses, but also maintenance operations. This means that the memory controller sends every DRAM operation and the DRAM chip executes every command. This means that everything is controlled by the memory controller and the interface is therefore very rigid. Now, to ensure reliable operation, modern DRAM chips require many maintenance operations. The paper talks about 3 of them. First, we have DRAM refresh. This prevents data loss due to charge leaking from the capacitors in DRAM chips or in the DRAM cells themselves. Next, we have RowHammer protection. This protects against disturbance errors caused by frequent activation of nearby rows. We already know a lot about this. Next, we have memory scrubbing. This periodically scans the DRAM rows and checks if there are any errors prevalent in the code and tries to fix that corruption if anything is found. Now, as memory continues to scale and gets smaller and tighter, we need more memory maintenance operations to allow the DRAM to continue to work reliably. Therefore, continuing to find new or develop new efficient maintenance mechanisms is integral. Now, the problem with this is that this is all controlled over the DRAM standard interface, and that is decided upon by JEDEC, which is comprised of over 390 companies, which have to make the decisions together, essentially, to decide what is not part of the interface. Therefore, changing the interface is a very lengthy process. For example, it took 5 years to go from DDR3 to DDR4, and another 8 years to go from DDR4 to DDR5. Therefore, the first problem this paper tries to solve is that there's a barrier for new maintenance operations as they cannot be implemented without a multi-year efforts. And the second problem is that there is overhead in maintenance operations, as DRAM is currently unavailable while maintenance operations are performed. And this means that memory requests are blocked, and this leads to performance degradation in terms of more latency and less bandwidth. This is a worsening problem since DRAM will probably continue to increase in density, and this will reduce the reliability of the DRAM. Therefore, maintenance operations will have to become more frequent and will also probably have to become more complex. Increasing efficiency of these maintenance mechanisms is therefore integral. Now, DRAM operations can be categorized into two classes. I'll explain this so that we understand more about how this will actually work and why it will work. First of all, we have accesses. Those are performed only to serve memory requests. So we activate a row to, for example, read or write to it. And the information of that is only available to the memory controller itself, as that knows which row and which data should be given to the DRAM. The second one is maintenance. And those commands are sent to perform maintenance within the DRAM chip to preserve data integrity. And the information that is actually used here can be found only in the DRAM chip itself. For example, for RowHammer protection, counters for how often a row has been accessed. Now, a key observation here is that the DRAM chip itself has all of the information it needs to maintain itself. And two benefits of an autonomous DRAM chip which maintains itself is, first of all, that there is faster, or there's a possibility to implement new maintenance mechanisms faster, as the DRAM interface does not have to be changed to facilitate new additions. And it also allows for more efficient operations. It will also allow DRAM manufacturers to perform their own architectural optimizations without having to release any proprietary information about their own technology. Now, a key challenge is that the DRAM interface is not flexible enough currently to accommodate any autonomous maintenance operations, as we are currently in a purely processor-centric control scheme or design philosophy. And the goal of the paper here is to enable autonomous maintenance operations with a minimal change to the DRAM interface. So next, I'll be getting to the self-managing DRAM system itself and explain how it works a little. So first, the problem of why we cannot just implement any autonomous maintenance operations as it is now is that, for example, if a memory controller were to send a DRAM command to the DRAM chip, which just currently decided to do maintenance on whatever region wants to or has to be accessed right now, then an access maintenance conflict can occur. This we would not want, as the memory controller currently would not know how to deal with that. Now, the mechanism that SMD implements or introduces is one signal, which will allow the SMD chip to simply reject any activation command that the memory controller has made. This means that work can now be partitioned evenly among the memory controller and the DRAM chip, as the memory controller can now perform all access operations and the DRAM chip can now perform all maintenance operations itself. To explain how it's actually built on the DRAM chip itself, I'll explain how this will actually work and how a DRAM chip looks itself. So we have a DRAM chip that has multiple DRAM banks, and each of these banks has DRAM subarrays. Inside of these DRAM subarrays, the physical rows are located, which have the data that we desire to access. And each of these DRAM subarrays will have its own lock region, essentially. This will allow us to address different lock regions concurrently. And to allow this to happen, it also introduces a lock controller and a lock region bit vector onto every chip. The lock controller just simply manages the lock region bit vector, and the lock region bit vector has a bit for each of the lock regions within a DRAM bank, and therefore knows which banks are currently locked and under maintenance. Now, how it works is that the microcontroller simply sends an activation command to a specific DRAM bank, or, well, in this new implementation, a region. And if this region is not busy with anything and just works as normal, then everything proceeds as normal as well. However, if the region is currently busy with a maintenance task, then a negative acknowledgement is asserted. And this just lets the memory controller know that the command did not execute. It then has to retry the same activation command after some delay. This is called the activate retry interval and can be found empirically. Now, in a more specific example, say we have a lock region 0, and we want to access something within that lock region. We then send this activation command from the memory controller, and the SMD chip returns a negative acknowledgement signal. Now the memory controller knows the access did not work and it has to retry. After the specified retry interval, it then gets to retry. However, within that time span, we know that the memory controller or other lock regions do not do anything else. Therefore, we can send another activation command within that time frame to essentially do work concurrently. This allows some level of parallelism in the chip itself. And the retry interval prevents indefinite locking, or just allows us to know that every memory request will be performed within finite time. There's a proof in the paper for why this is the case. However, I won't go into that. Now, the key benefits, I will quickly go over them again. First of all, SMD allows for more flexibility and innovation, as DRAM vendors can now implement or modify any maintenance mechanisms that they want. Due to the maintenance latency overlaps, we have a better performance. As we decouple DRAM from the operations itself or from the interface, we have higher modularity, and we can also assume that there will be forward compatibility, as essentially anything can be implemented without having to rely on the interface at all. Now, I'll talk about a little about the maintenance operations themselves. In SMD, every maintenance operation will be done within or on the memory itself. The benefits of this are that energy consumption is reduced, as way less commands have to be sent over the memory or over the command bus. For example, in DDR4, within 64 millisecond, 8,192 refresh commands would normally be sent. This will not happen within SMD. This means that data movement is minimized across data or across memory buses, and this therefore also improves performance by avoiding any contention and latency introduced by sending commands. Now there are three memory controller driven maintenance tasks that are implemented and described thoroughly. First, we have DRAM refresh. There is fixed rate refresh and variable refresh. However, I will just talk about fixed rate refresh. Then we have RowHammer protection. There we have probabilistic RowHammer protection, which was tested, and deterministic. However, I will be only talking about deterministic briefly. And we have memory scrubbing, which on rank level just performs ECC, which I'll also briefly talk about. So first we have the fixed rate refresh. This is, although this looks quite complicated, it's actually quite simple. We have the pending refresh counter. This just makes it so that new refreshes will be performed. Then we have a lock region and a row address counter, and these just decide where we actually will perform the refreshes. So if that pending refresh counter is above 1, then we try to lock whatever region is currently under or should currently be under maintenance. If that succeeds, then we refresh that row, release the locked region, increment whatever whatever position we're currently in, and then decrement the pending refreshes, and then everything happens all over again. Now this is also looks very complicated. However, it's essentially just that we have a counter table, and every time a row is activated, the counter is incremented, and after some threshold, the neighboring rows will be refreshed to hopefully mitigate RowHammer. And rank level memory scrubbing just performs ECC or error correcting code on any potentially corrupted addresses or rows. And this implementation uses or would use something similar to what was implemented in DDR5. So it would use something that's already implemented. Now I'll get to evaluations of the performance of this. However, first I'll talk about the actual implementation that was used for the simulations. There we have two options as to how this negative acknowledgement signal could actually be sent. First, we could use an existing pin, which would be alert N on the standard interface, and that would have no cost. Or we could just add additional pins for each DRAM chip. This would add about 1.6 pin processor pins. Now, on a 45mm squared DRAM chip, we will have to implement the lock region bit vector. This was essentially the register that remembered which lock was currently held or which regions currently aren't accessible. Then we'd have to add new row address latches. This essentially allows us to perform the maintenance accesses in parallel or concurrently with any rejected memory accesses. And then we would have obviously the maintenance mechanisms that are implemented, and these would wildly vary depending on whoever implemented them. In the memory controller itself, there are also a couple of modifications that have to be made. First of all, 288 bytes of storage. These will just keep track of the locked regions. And then the existing memory request scheduling logic could be reused. However, I do have some qualms about that. Everything was simulated using Ramulator. The base system configurations are a 4 GHz 4-core processor and DDR4 3200 MHz RAM. And the SMD parameters used are 16 lock regions with 16 subarrays each and a 62.5 nanosecond return interval. Those were found empirically through testing. So the paper compares multiple system configurations. First of all, we have the baseline DDR4 system. This is just any normal computer essentially you could find anywhere. Then we have fixed rate refresh. This only implements the refresh. Then we have deterministic RowHammer protection. This implements the RowHammer protection along with fixed rate refresh. Then we have the same with memory scrubbing and an SMD combined configuration, which just combines all of these. So that would, in practice, be something we could actually work with as it has all of these maintenance operations. We also see that they used a DDR4 system that does not have to do any maintenance and is therefore theoretical bound as to how good it can get. The single core performance we can see is about 4.8 to 5% of an average speed up above the base configuration. In specific, I would like to highlight that the SMD combined configuration achieves about 84.7% of the speed up of the no refresh, so the hypothetical maximum. We see something similar in the 4-core performance. SMD provides higher speedups with increasing workload of the memory intensity. And we can see that On high workloads, this reaches almost 10% speed up. And again, is very close to our theoretical maximum. Now, in terms of energy savings, this SMD also saves a lot of energy, obviously not in the low system or low load, as there are not a lot of operations that have to be done. However, on all other types of loads that were tested, SMD combined provides about 60% of the energy savings of no refresh, and that would be about 96% of the energy used by the normal DDR4 chip. Now, we see SMD provides performance and energy benefits that are comparable with a hypothetical maximum or best system that doesn't have to do any work. And the benefits over the baseline here are attributed to overlapping the latency of memory of maintenance operations with access operations, so that we have some kind of concurrency, and reduced command interference and energy use, as the MC doesn't have to issue any maintenance commands. Now I'll come to my conclusion. It's difficult to see because of the thing. However, on the DRAM interface design scale, we are currently on the very left side, completely processor-centric control. However, we were trying to move into the direction of DRAM-centric control, which I think this would put us about at the middle. And new maintenance mechanisms require changes to the DRAM standard. We already know that now. And with SMD, implementing any new maintenance operations would no longer take any additional time in company politics or JDEC politics. And we observed that 3 high-performing maintenance operations could be implemented on SMD, which all yielded benefits over the baseline. Now to the critique of the paper. Those are the strengths. I believe that SMD is an innovative approach to shift away the DRAM management from the memory controller and allow for more DRAM-centric control. SMD's versatility is also showcased through 3 very common maintenance operations. We just saw that SMD provides performance and energy efficiency, which are close to a hypothetical system. And we have also seen that there would be minimal interface changes required to actually facilitate this change. Now, to the weaknesses, I kind of categorized them into classes. So here we have a weakness that it would add hardware complexity. The paper doesn't fully address how reliability could be impacted by adding logic to the chip. For example, if logic is on the chip, then that means that there would be more heat on the chip, which could reduce reliability of the chip, which would then require potentially more maintenance operations to be performed, which would kind of be against what SMD is trying to achieve. Then there's also negative acknowledgement divergence. And that is essentially that if we have a chip or if we have a memory rank that is split among multiple chips to increase data that can actually flow through the data bus, then if some of those, for example, were under maintenance and others weren't, then that would mean that the memory controller, again, wouldn't really know what to do. And any of the proposed fixes to this would also, as with the prior points, kind of go against the purpose of what SMD is trying to achieve by either increasing energy or decreasing time. Now, the paper also doesn't thoroughly analyze whether SMD could introduce any new security vulnerabilities, though I feel that is quite a weak criticism. Next, we have the interface change itself. while minor, there could definitely be a snowball effect, which would affect multiple other system components and could facilitate huge changes in those. So those would also have to be regulated, and that could also add a lot of time to how long it would take to actually implement this. Then there are economic considerations. The paper doesn't address possible cost implications to the manufacturing, research, and development of the DRAM manufacturers, or discuss other adoption barriers. And then there's also testing considerations, as could potentially be very expensive to do tests to see or to check if those maintenance operations are working as intended, essentially. And then another problem is that SMD makes the interface less predictable, as memory requests can be essentially at random be rejected. This leads to unpredictable latency spikes, which could impact real-time workloads or anything memory critical. And then there's also system-level integration, and the paper doesn't really go into how this could potentially change the system, or higher or lower system changes needed to accommodate this. Now, before I start the discussion, are there any questions? Apparently not. My first question I would like to ask you is, well, isn't really a really introspective question, however, was the first that came to mind. Why is this, or why has this not been implemented in any form up until now?
Because of the magnitude different costs of long-term reliability.
Yeah, that could definitely be a problem that could be introduced. Anything else, or anybody else?
You want to use this?
Maybe the standards, the manufacturers have to challenge the standards that is chosen by the JEDEC, like the corporation. So because of these challenges, as well as they don't know how much economic throughput that will put, or maybe how much is this viable, is it a viable option to produce those type of chips economically, maybe, as well as it also has to challenge some of the production standards, which also maybe they have to implement another manufacturing processes to change this, which is maybe not economically logical for the manufacturers the major manufacturers that we.
Yeah, those are some good points. I have something along those lines as well. However, are there any other ideas, or should I continue with my own points I have here? Okay. Yes, so my first point is essentially what you said. The DRAM vendors could just decide to not want to implement this, whether it is, for example, cost in manufacturing on the die level, or having to change ways of fabricating memory itself, or if they believe it would, for example, introduce problems in the ecosystem they already have established, or, for example, if they feared that this could also expose some like worse worse maintenance operations they personally implemented, and fear this could hurt their market share. However, we could also say that there is no real-world proof of if this actually works or not. Everything this paper has proposed is purely in simulations, and in any case, this idea still lacks maturity. And then it could also implement the markets. So that is another point of why companies might not be interested in implementing this, as this could increase the prices of DRAM, and that would also harm market share to some extent, as consumers might not be as interested in buying more expensive equipment. The next question I have is about the performance predictability I just addressed. Since in real-time systems, predictable memory access latency is very important, how might the semi-asynchronous nature of SMD affect these time guarantees?
I would think that since everything is done on board chip, you could have sent like a small little flag to the CPU every so often just to notify, hey, now is the maintenance being done in case you ever want to do any memory type stuff right now. Give it a second. Would be a possible way of giving some more predictability to it.
Yes, that would be something that could be done. However, that would also kind of defeat the purpose, right? Because that would again like fill either some extra signal or the command bus itself.
But I assume it'd be less than the entirety of having signals being constantly sent back and to from the host, like a small little one, maybe.
That is definitely a possibility, especially since the memory controller in this implementation also has the information, or rather registers of which regions are currently locked. So that would definitely work. Anybody else? Yeah, so that was a good point. However, I would just address some further problems. For example, in real-time systems, we have things called service level deadlines. These essentially just expect data to be there at some specified point. And as I said before, this cannot really be guaranteed, as seemingly at random maintenance could be done. And also the divergence across chips which would also just increase latency and could add further time or further latency spikes, which would again not be predictable. Now, the next question I have is about maybe future maintenance operations or just different things that could be done using SMD. So beyond the 3 use cases presented, what other DRAM reliability or just performance challenges might benefit from the approach, or what could also be implemented? Anybody? Okay. Well, I had a couple of ideas of what could be implemented. For example, I immediately sprung to processing in memory, as the locking we have here would not only allow maintenance operations to be performed independently, without having any like access conflicts, but it could also be used to add logic to schedule or just perform some operations inside of the memory itself. I think that would definitely be a possibility. Another thing that could be added, along with just adding logic to the chip, is adding in-DRAM prefetching or just more data awareness inside of the DRAM chip itself. I think that scheduling could be used to have that work with SMD as well. And then I also thought of some security applications, for example, either just completely locking regions down without having any sense of access to them through just the locks and the scheduling that would be introduced. Or, for example, having the DRAM chip securely completely like flush DRAM rows and like delete data that could be critical and just wants to be deleted without any trace. Now, another thing that SMD managed to improve upon is energy management. And here I wanted to ask what SMD could potentially add or implement that would allow for better use of energy or just less use of energy. To the right.
Maybe there'd be a way to have less restrictive refresh interval, because I know that the vast majority of bits don't require as frequent of a refresh, but we need to ensure reliability, so it's very conservative. So maybe there would be some way to get internal feedback and slow down the refresh interval.
Yeah, that is actually a thing that has been talked about in the paper, but I decided to omit, as it's essentially just the interval or this normal row refresh that we have with added logic to skip rows that aren't seen as like less capable of actually carrying information. I do have a slide here, but I think I won't show it because it's just another pretty like complicated looking flow diagram. But that is definitely a way to improve energy usage. Anybody else? Okay, I'll move on then. Some other things I thought about was fine-grained power down regions. Essentially, we could use the locking of regions to completely disallow rows to expect any activation commands and just merely focus on the bare minimum to refresh the rows. We could also add some kind of temperature sensors on there to allow for temperature adjustments in each region. And for that, for example, we could use logic on the chip to move rows that are frequently used and therefore warm or pretty hot to less used places. Now, the next question I have is, what are long-term implications of shifting more intelligence into the DRAM chips, and how this might change the evolution of memory controller design and memory design in general? Okay, so I believe that such changes could definitely allow a shift towards more data-centric architectures, as this is the first step towards allowing processing, or at least giving some responsibility to the DRAM chips itself, and not having every operation be done in the processor itself. This would also just allow to distribute control across chips, and it would shift, or it would allow others to think about memory as something else than just a passive entity which performs energy, which performs DRAM commands. Now, I have another question. How would SMD ensure that data which is rejected as an activation command given that SMD aims to accelerate innovation in DRAM maintenance operations, how might the JEDEC standardization process itself need to evolve to accommodate to this new paradigm? Are there any people interested in contributing?
Yeah, so DDR6 might have some extra unused pins that could be used by an updated DRAM chip or updated controller to implement some more logic, so that we don't have to wait for DDR7. Yeah.
Well, I think that somewhat goes along what I would talk about. So I think that it would definitely change towards JEDEC, assuming more DRAM controller driven behavior, and about what you just said, it would, like, adding pins essentially would allow us to have tunable parameters inside of the SMD, which could in this case be addressed. For example, the retry interval over the standard interface in this case. I assume my time is almost up, right?
No, I think you can conclude.
Okay. So, I mean, I think I have one or two more questions. Or this is probably the last. So how should system designers balance security guarantees, such as more aggressive protection or more refreshes against performance impacts? This could also play into the other weaknesses I mentioned, which could be fixed by using more energy or using more time, essentially. Are there any people who want to say something?
I mean, it depends on the operation or the user, I would say. If they want to have more security guarantees, that means that the system will probably use more energy. But if we are going to talk about like low energy architectures or low energy systems, then probably our security guarantees will be a lot lower. So it depends on what the user wants. So in that case, it depends, I think.
So you're saying there should be tunable parameters, as I just proposed?
Yeah, maybe everything comes standard, but users can, modify some of the parameters to, to their liking. If they want, higher protection, then the system probably use more, energy at the end. But if they want, less energy, then they'll need to opt for lower security guarantees in their system.
Okay, so should the chip then have all of the security inbuilt to allow the user to decide, or should each manufacturer get to decide on their own what they are interested in essentially making?
I mean, the customer is king, but it all depends on the producers or the manufacturers. They can maybe manufacture all of them, and then the most expensive one will be probably the most configurable one. But then, yeah, maybe it can also do plug and play, or if you want to consider something different after some time, you can maybe add some more components to it. It depends on the operation or what they want.
Okay, so just user experience essentially and feedback, probably, right?
Yeah, probably.
Okay. I think.
If previous operations were done are recorded statistically, and the maintenance processes are adapted to that recorded information, then in most of the high demand operations, or specific most operations would follow a certain pattern, would reduce activity, thus increase average performance.
So you believe that it should depend on the operations that are like performed in like essentially real life or in trials to see what's best?
Operations that were performed before in the system.
So just
time frame.
Okay. I'm not quite following. Okay. So yeah, obviously stronger protections would reduce vulnerability. However, that could hurt latency and throughput, which would have to be considered by the companies. However, I personally believe that system designers should be able to tune this and not have any more regulations imposed upon them to allow for further progress. However, I do think that for critical systems, it definitely should have some regulations, although I probably believe that those shouldn't be made by JEDEC, but some other company or some other group of people who actually will work with these critical systems. So I'm through all of my talking points now, and I would like to thank you for listening, and I would like to thank Ataberg and Andreas for helping me prepare this presentation.
Thanks a lot.
And this is the thing you talked about before. Okay.
No, you go ahead. Okay. I thought you would make something.
Okay, thanks for the nice presentation. Is this working?
Yes.
Can people hear me?
They can hear you online.
Oh, online. Okay. Can online people hear me? Okay. So
Yes.
this I think it's good that we started with this presentation because this paper proposed a very simple, small change, in my opinion, that is a no-brainer, but it's very hard to get it adopted because of the huge dichotomy between processing and computation in modern systems. In a sense, this is actually one of the biggest troublemakers in our industry, in my opinion, which is you have compute, you have memory, and the interface between them is completely broken. Basically, the interface is completely controlled by the compute unit, and memory units cannot do anything at all. And you asked why this is not implemented. One of the reasons why it's not implemented is because it's a new idea. It was published in Micro 2024 because it was rejected 6 times before. Micro HPCA ISCA, Micro HPCA ISCA, and then finally it got into Micro. This tells you something. Not much has changed during those 6 times. Basically, the idea is the same, evaluation improved, but it's basically you can see that this is a research conference. It's not even implementation. There's huge resistance against something like this. I mean, if you're so resistant against an idea, imagine how resistant you would be in industry implementing this, right?
So I assume it's quite controversial then, as I would think there's a lot of different people who try to implement something.
No, I think that the controversy is really, we don't do anything intelligent on the memory side, basically. That's the only controversy. Industry has evolved that way. People are comfortable that way, and it limits a lot of innovation, as we show in this paper. So there needs to be some will to change this system, basically. And I hope that will come over time, but you can see that a simple idea like this is very difficult to push through, even in the research community. Forget about the industry yet. But I believe something like this makes sense, and I think it's a very principled design. It's a move toward the right direction, and people need to keep pushing. Some of the ideas, for example, some of the questions you asked are very good, and those are good research topics, right? I don't think there's an issue with predictability, because if you really want to have a real-time system, then you disable SMD, right? And there should be ways of disabling that. So it should be a flexible mechanism, and the aggressiveness level can be configured. But I think there are a lot of interesting research can be built on top of this. Maybe it'll be implemented 30 years down the road when people want to actually save energy and do real high-performance computing. Well, as opposed to get around it today or try to get around it.
Seems it will be necessary at some point.
Exactly, right. If you think about, like earlier in a lecture I talked about systolic arrays. The idea was proposed in 1970s, and now it's implemented in many machine learning accelerators 40 years later, 40 plus. Good to think about that. So our goal is to really long term, not the short term. And this is one of the toughest part of the interface. If there is a really huge part that's limiting computing today, it's really the memory, how we treat memory and how we access memory. It's really that interface. And I think we need more people pushing new ideas in that direction. Okay, that's my end of comments.
Anyone else? The mentors, maybe? Do you want to add something? Okay. But then I would recommend that we move on straight to the next one, probably.
You're the boss.
Okay, then let's switch.
Small addition.
Please.
the industry is kind of making similar changes, especially to mitigate RowHammer or read disturbance errors. With a recent addition to DDR5, we have per row activation control. PRAC already implements one or makes a similar simple change to this interface to basically tell the memory controller to give it some more time, the chip more time to perform some refresh operations internally. It's not as abrupt as what we propose in SMD in terms of like how you interrupt the memory controller, but SMD can also implement the interrupt signal in that way as well. Basically, the industry is also not resisting the innovation at this point. It's just the research community that's resisting for some reason the innovation. Yes, so.
I don't know, we can have a discussion about that. But because of RowHammer, yes, I think the interface has changed a little bit. But they had to take RowHammer seriously because a lot of other industry pushed the manufacturers to take it seriously because of a lot of papers written on the topic. So the main mode of operation in memory industry is don't change it. Which is not good for innovation, as you can imagine. That's good, we can discuss these things.
Yes, I understand.
They haven't yet made it the academic institutions to stop discussions.
Let's ask him if he wants.
Would you like to see your presenters now, or would you like to take the screens?
So see the same as that, or do you want to know?
No, that's fine. I just need maybe see the time. So I don't need to read the house, but maybe just sit during this.
Okay.
No. You have to wait.
Okay, thank you. Okay, so this is the second paper of the first session. This is a really fresh paper out of the, it's freshly baked. It's just presented earlier last month in HPCA. So the first author is Ataberk, who was making comments on the other paper recently. So if you have really tough questions, you can ask him as well, but please feel free to grill Alp as well. So Alp Tuzum will present this paper. He's a first-year master's student in the computer science department, and he is in the track of secure and reliable systems in that master's program. And his research interests include cybersecurity, cryptography, and computer architecture, so it's very relevant. And I'm not going to talk more, and I'll just leave it to you.
Okay, thanks. Thanks for the introduction. So let's start. So I'd like to start with some executive summary of this paper. So the motivation was that current solutions all depend on heavily accurately determining these disturbance thresholds, and DRAM chips are currently also susceptible to disturbance errors. So the problem here was that no existing studies explore this temporal variation of these threshold values. So the goal of this study was to experimentally analyze and characterize the temporal variations of with disturbance threshold in DRAM via an experimental setup where they tested on different DDR4 as well as HBM2 chips under various conditions. And the results show us that these threshold values can significantly and unpredictably change over time. As such, data patterns, aggressor times, as well as temperature influence these threshold values with no specific correlations. As a result, the authors suggest that combining threshold values with some guard bands, along with some error correcting codes, can mitigate these bit flips, but also introducing also some additional performance penalties. So here's the outline. I would like to start by the background, give some refreshers about RowHammer, RowPress, and also with disturbance threshold. So let's start by DRAM organization. So as we all know, DRAM consists of memory channel, ranks, chips, and banks. And each bank has a row and column of cells which can store 1 bit of information. So when a row is opened, so its word line is asserted, its cells connect to the sense amplifier, so the row buffer via the bit lines shown here. And because of this operation, as well as DRAM cells' current architecture, these cells can leak charge over time, so we require periodic refresh operations to restore their contents. As such, we also have read disturbance errors. So I would like to talk about the first one, RowHammer. As we all know by now, RowHammer is a read disturbance error, where aggressively activating a row so many times in a quick span of time can induce bit flips in a neighboring row. So it's a circuit level failure that can break the memory isolation assumption, meaning that even though we cannot access some specific cells, we can still modify its content, as shown here. And we also have his brother, which is RowPress, but instead of quick activations back-to-back in a short span of time, we try to keep a long-held activations until we can induce a bit flip in a victim row. And also we have this term read disturbance threshold, which is defined after the RowHammer and RowPress studies, which can be defined as a disturbance metric. So it means the minimum number of activations that it's needed to trigger a bit flip in a neighboring row. So simply a row's threshold value is the activation count at which it causes an error in a victim. And the current mitigation strategies, we have assumed that there is a constant worst case threshold value. Therefore, we have to measure these values. And it's typically identified right now by doing exhaustive read disturbance testing. And we also have some mitigations against these attacks, such as para, targeted row refresh, or proposals. And they all try to prevent these errors by intervening before aggressor reaches some activation count. In case of para, we issue random refreshes with some probability, or in TRR, we track aggressive activations. But all, in essence, all of them have a common intuition that all of them assume a fixed activation count for these rows. So now I would like to talk about the motivation and problem statements of this study. So the motivation was that we saw that this disturbance has implications for system security as well as the memory isolation assumption. So as also the DRAM technology scales, so the density gets higher and the nodes get smaller, the number of hammers for the first bit flip also shrinks consistently along the time. If you remember this figure from the lectures, you will know. And so our problem statement is, we saw that current studies lacks a research question. So does these read disturbance threshold changes over time? And if so, how accurately and efficiently can we measure them? So the goal of this study, in essence, was to experimentally assess these temporal variations of disturbance threshold values in a DRAM. So I'll also show the experimental setup they also used. So the test setup is based on a DRAM bandar infrastructure, which is an open source infrastructure implemented by Safari to test different types of conditions for each DRAM. So in essence, it consists of host machines, FPGA board, temperature sensors, as well as controllers, like shown here. So we had the DRAM module, which is wrapped by heat pads, which can be controlled by the device here. And we also have PCIe connection to our host machine, as well as the FPGA board that we use here. So we also test 160 different DDR4 chips, as well as 4 HBM2 chips from different manufacturers to investigate whether this phenomenon is affected by chip design or is a common occurrence across all manufactured chips that we have. So in our tested methodology, we try to correctly measure our thresholds for the chips for the worst case scenarios. And to achieve this, we first try to prevent source node interference, such as the data retention failures, as well as on-die countermeasures. And then we try to finish each measurement within a refresh window. And within these refresh window, we typically disable the periodic refreshes that are issued. And lastly, we use double-sided RowHammer and RowHammer access pattern, which alternately activates two aggressor rows adjacent to a victim row, like shown here, like a sandwich model, maybe we can say that. So I will also now try to talk about the key results and the findings of these experiments that they conducted. So before going further, I would like to also explain the testing algorithm. So our testing algorithm tries to first identify a row that is somehow vulnerable to the read disturbances. And after selecting this row, it tries to repeatedly measure for read disturbance values using varying hammer counts. And at the end, this experiment yields us 100,000 read disturbance threshold measurements for that selected row. Now I would like to enter the key findings here and share the results of these experiments. So our first key finding was that a DRAM row's threshold value changes over time. So to illustrate this, the authors constructed a box and whiskers plot for a single row in each chip. And to illustrate this, we can look at the first example. So if we can look at for chip 1, we can see that these threshold values changes over time. There is a variance among the measured threshold values. And if you look at the general idea of across all 14 chips, we can assess that all of these chips show or experience some kind of variation among these threshold measurements. And if we also divert our focus to chip 0, for example, the minimum and the maximum threshold value we calculated differs by a factor of 1.2. As such, we may also look at the characteristics of a single row within that 100,000 measurement. Also, we have a single row here, and this row shows its threshold, minimum threshold value only after 17,000 measurements. And if you look at the general view, that across all rows from all chips, the smallest value that we calculated appears only after 95,000 measurements, which is a huge number. And also, if we divert our focus to the last 1,000 measurements we have, we can visually confirm that these threshold values are not consistent across the consecutive measurements, and there is a visible variance among these measurements. And that brings me to the second key finding of this experiment, that these threshold values has multiple states. And to illustrate that, we may assign each measurement a state. So if these states change over time, if these values change over time, we can say that there has been a state change. And this here we have the histogram for a number of measurements across which a row's threshold value exhibits the same value consecutively. And we can clearly see by looking at the bars that the consecutive measurements yield different threshold values across consecutive measurements that we do. And we can also share that 79% of these changes happen after each measurement. And as we also increase the number of consecutive measurements, the probability that these measurements retaining their same threshold value also decreases across the board, such that keeping the same value for 14 consecutive measurements is a very unlikely event, that there was only a single lobe that could achieve this feat. And that brings me to the third key finding, that these threshold values frequently change over time. As next, the authors also wanted to assess the variable read disturbance and its predictability. And what they found out in this case is that these threshold values change over time in an unpredictable manner, such that we have here a histogram of threshold values for a single victim from each chip. And if you have taken your statistics class, you might see that there is a pattern here, that these histograms resemble some kind of a random discrete probability distributions. And if we look at the big picture for all 14 chips, we can conclude or come to realization that all of these resemble some kind of a random probability distributions. And this means at the end that given the outcome of the past measurements, the outcome of the next one is likely cannot be predicted. As next, we also wanted to look at the possibility of correlations across the measurements that we did. And to achieve that, they also implemented autocorrelation functions on the threshold measurements and also on the normally distributed random variable. And what they found out that these threshold measurements that are implemented on autocorrelation function is not different than the results that is implemented on a random variable. As such, we can see that the values or the patterns are when we compare them, there isn't any difference among the single chips row and a Gaussian normal distribution. And that yields the fact that these measurements likely have likely have now repeating patterns. And we can also see the measurements for that row in that chip M1. So the key takeaway from this finding is that these threshold values changes randomly and unpredictably. So it's a hard task for the researchers to reliably and accurately determine these thresholds over time. As next, they also wanted to assess parameters, combination of parameters, the permutation of parameters and their impact on these threshold values as well as variable characteristics. And to achieve this, they tested 150 DRAM rows from each chip across different timing values as well as different temperature parameters. I listed the timing parameters also that they picked here. And to assess this, they used a metric called coefficient of variation. The goal here is to observe the behaviors across different conditions, meaning across different permutations of environmental variables. So a higher CV value indicates there's a larger variance amount of mean threshold value that was measured. As such, they picked two rows, one of them exhibiting a CV value of 0.52, which was the highest recorded across all test runs. And on the left side, we have a CV value of a row that exhibits a value 0.03, which was the median value when we sort all of these results. And we can say that on the right side, the minimum and maximum threshold value can differ by a factor of 3.5. And on the left side, they differ by a factor of 1.2. And that brings us to the fact that all these tested rows exhibit some temporal variation. So all these tested rows, as a result of the previous experiment, have a non-zero value in at least one of the test combinations that we picked. And the maximum C value, like I said, was 0.52, and 50% of the rows have a greater variance than 0.03. And to conclude, 97 of these tested rows under all test combinations that we picked, the values vary across the measurements that we did. And in contrast, there exists, for the rest of the tested row, there exists a single combination at least that yields the same threshold value across different test runs. So that means that a large fraction of these tested rows exhibit variation across all parameters. And the researchers, as next, wanted to ask a key question. So measuring these threshold values is similar to sampling from a normal distribution. So can we identify this minimum threshold of a ReRAM that it exhibits after 1,000 measurements by doing maybe less than 1,000 measurements? Is this a possibility? They want to look into this fact. And to look at this, they constructed Monte Carlo simulations. So what Monte Carlo simulation does is that it does repeated random sampling to estimate outcome of a process. In this case, our key question. So in each iteration, we uniformly randomly select n measurement, n being from 1 to 500. And at each test, they wanted to demonstrate how the probability of finding this threshold value, as well as the expected normalized value changes with the number of measurements that they do. And as a result of these simulations, they constructed a probability distribution table across different number of measurements that they can pick. And what they found out is it's very unlikely to find the minimum threshold value by just doing a single measurement. That means that you have 0.2% chance to find this ground truth value. As such, by also doing a single measurement, you'll also experience very large variation across the board, as visible here. If we pick just a single measurement value, our probability starts from 0 and extends continuously all the way to the probability of 1. We can also clearly see here that the probability of finding these threshold values increase with the number of threshold measurements that we do. So if we increase our number of measurements, our minimum probability also increases, as well as our variation gets lower across the board. So that brings me to the second key takeaway from this, that few measurements are unlikely to identify the threshold value that we search for. Our estimations
can become more accurate if we increase the repeated measurements. But even at 500 measurements, our minimum probability isn't still high enough to come to a concrete conclusion about this. As last, the authors want to also assess the effect of change temperature as well as change timing and its effect on the VRD profile. As such, VRD profile varies across these tested chips. So the profile worsens with increased die density as well as more advanced DRAM technology. And there isn't any single data pattern as well as aggressor time that causes the worst profile across all tested chips. And that brings me to the third and final takeaway, that data patterns, temperature, or aggressor times affect VRD profile in an unpredictable way. So as a result of these experiments and these key findings, we have implications for our security as well as current mitigation strategies. So we saw that if these threshold values can surprise us, meaning they change over time in a random manner, any mitigation that relies on the measured activation counts or threshold values can fail abruptly over time. And identifying these minimum thresholds after even doing maybe 100,000 measurements is a challenging task because these threshold value changes in a random manner. So we have to accept the fact that if we cannot precisely identify a stable threshold, we have to accept that some bit flips might occur. And in that case, we have to implement a safety margin to the calculated threshold values. And as a result, the authors come to conclusion that more than a 10% guard band for the measured threshold value, along with some error correcting code, could prevent some of the bit flips, but it comes also with the cost of the additional overhead we have. So a threshold value that is used to configure a mitigation strategy cannot be larger than the one experienced. As such, your mitigation strategy will never prevent any bit flips. And also it should not be significantly smaller than the experience so that your system is not getting punished excessively. And there are also some challenges when implementing such mitigation strategies or solutions for the future. So we saw that difference between the minimum as well as the maximum threshold value can be more than a factor of 3.5 or may not be even bounded if we may have been able to do maybe around millions of measurements. And we saw that it requires hours of testing. So to profile a single bank of 256,000 rows, it takes us 39 minutes to do under different parameters, which is in fact not scalable to the rest of the DRAMs that we may want to profile them. So as a result of these conclusions, authors want to also assess the guard band approach and want us to see how much overhead they may introduce on the current strategies. And to do that, they evaluated the guard band approach on state-of-the-art mitigation strategies against read disturbance errors within a DDR5-based simulator. And they saw that overheads increased with the larger guard band. And if we also want to implement a safety margin of 50%, which is a conservative approach, our system overhead substantially increases. So if you look at this normalized system performance graph, the red line is the desired system performance. But as we implement a margin on top of the measured thresholds, we are systematically punishing our system by introducing more overhead, or in this case, maybe more refreshes, which lowers our system performance. As next, they want to also see the effectiveness of doing just guard band implement solutions. To do that, they constructed also the probability table that includes the minimum probability with the bars and the mean probability with the circles across different number of measurements with different number of safety margins that are implementable. And we came to the conclusion that if we do 50 measurements, the average probability of finding this threshold value is around 99% by just adding a safety margin of 10%, which seems really nice, in fact. However, this is a wrong conclusion about our solution, because using margins alone is likely not effective at mitigating VRD-induced disturbance, because even if we did 500 measurements and implementing a conservative margin of 50%, our minimum probability is still not high enough that we can conclude that this guardband approach is really really nice, as well as if we implement a 50% of margin, we saw that our system overhead increases substantially. So in that case, we have to deal with some bit flips to create a feasible solution, but without introducing a huge system overhead. And to assess this feasibility, the authors also constructed a histogram that shows the distribution of number of unique bit flips across all tested flows if we just implement a safety margin of 10%. And we can see there are at most 5 unique cells that experience a bit flip in a single ECC code word. And the likely outcome here is that we are going to experience just a single unique bit flip by looking at the histogram distribution of this unique bit flips. And because there's most likely outcome is we're going to experience a single bit flip, these patterns are more likely lead to something correctable with some single error correcting and double error detecting schemes. And also, if we implement a margin that is larger than 10%, we are going to experience no more than a single bit flip in our code word. And now I would like to discuss and start the conclusion part, share the key findings again, maybe. So we saw that this work contributed to the observation of variable read disturbance, as well as its first-time assessment under a serious experimental methodology. And it's also demonstrated that a Row's threshold value cannot be easily be identified, and also challenged the previous core assumptions about the mitigation strategies. And we saw a possible solution will require us to tolerate some of the bit flips via maybe error correcting codes or message authentication codes on top of our selected guardband we want to have. And the last results have indicated that using a 10% guardband for the observed threshold value and error correcting code could prevent the bit flips, but may not prevent all of them due to the limited measurements and the conditions that these work have considered in their test rounds. As last, the authors also give 3 directions for future work. So in the future, we can gather more data by performing more measurements, of course, testing more chips under a variety of new, maybe environmental conclusions to come to our more reliable conclusions, and as well as maybe more comprehensive solution that considers additional factors. And we can also develop online profiling mechanisms such that they can measure these threshold values while chip is in normal use to mitigate the long profiling times that we have shown before. And lastly, we can also develop mitigation techniques that can dynamically configure themselves by using the online profiling mechanism that we would like to implement also in the future. So that brings me to the end of the paper review. Now I would like to share the strengths and the weaknesses of this paper, in my opinion. So the first thing I want to talk about is that it gave a novel insight and a new perspective with disturbance error research. So it discovered that unreported or maybe an ignored phenomenon across this sector. And in its essence, it challenged the core assumption that these threshold values can be correctly measured or they are stable after each measurement. So at the end, it cemented itself as a seminal work, and I believe it's also reference for future research in the with disturbance mechanisms research. And it also had a comprehensive experimental methodology that tried to cover everything, every conditional or every corner case. So they have tested very large sample of chips. So at the end, it helped to cover the extreme cases, and come from these results of these extreme cases, it come to a general conclusion about this phenomenon. And we also saw that the environmental factors are varied in the study, which has to claim that this is a common occurrence. Though VRD is something common, that it is not something that we should be observing by chance or some randomness. So at the end, it prevents the false positive assumptions that we may conclude about this study as well. And also, I like the fact that these experiments are reproducible in design, meaning that the infrastructure we saw was an open source. So if we can construct this infrastructure and gather these chips, we can also reproduce the same results as well that was discussed in this research. And lastly, I would like the clarity of finding as well as the coherence and the discussion about these results. So we saw that the paper lists 17 findings, which unfortunately I couldn't discuss all of them. And it groups some of these findings under some key takeaways, making it easy to understand the results that we saw. And also we saw that the findings are all backed by data. So they use statistics such as mean, median, range values, as well as simulations examples to make the phenomena concrete. And I also like the fact that they considered the worst case scenarios as well as average case scenarios, which is important. So when we design a mitigation strategy, we want to consider the worst cases as first, and then try to improve the solutions by looking at the average case scenarios and try to improve and build upon them. So I would like to now enter the weaknesses part, so critique the weaknesses of this paper. So I think there's firstly, there's a weakness in the feasibility of the suggested direction. So we saw that exhaustive profiling is impractical in approach because it consumes a lot of time. But however, the suggested online profiling is also impractical in the sense that because they didn't give any clarification or in-depth explanation that separates these two approaches, and such that an explanation would have been more meaningful to also create a better future direction such that differentiates these approaches, as well as creating, dissipating the confusions that maybe arise about this question. And also, it has a weaknesses on reliance on one of our row at a time characterization. So the measurements we saw just focus on a single row. And I believe there could be a potential that these grouping rows together during profiling times could matter in the sense that if we can group these threshold, these rows together and calculate these sum of the values or threshold values from a single element of the group, then assign some values maybe to the other parts of this group, we can speed up the profiling time. So any exploration on this topic improve the solution with some higher performance and less individual treatment for each row. And as last, I want to talk about the suggested mitigation and its limitations. So the guard band and HPCA solution isn't really different in terms of probabilistic approach from the current solution, meaning that with some probability, our solution still could fail to mitigate some of the bit flips that we can experience. And if you want to also lower the probability of such events and try to be really conservative about it, such as implementing a 50% guard band, we are going to experience up to 45% performance loss, which is a huge bottleneck to our system. And we can also talk about the fact that some of the chip manufacturers have claimed in the past that their RowHammer and their chips have defenses against RowHammer or row press attacks. But as the time passed, researchers have come up with sophisticated techniques to circumvent these countermeasures. So in this case, these countermeasures could also work again. These attacks could also work on this approach. And if they can possibly do multiple bit flips, in the end, our solution will be nullified. So at the end, I believe this is likely a preliminary exploration, meaning that it's a temporary solution rather than a full-fledged or standalone solution that they need to suggest. So before going to discussion, I'd like to also share the key takeaways of this paper. We saw that variable weight disturbance is a widespread and unpredictable phenomenon, such that a row's threshold value can vary significantly and randomly over time, meaning it challenges the previous assumptions that we made about the mitigation strategies. And the paper's large-scale experimentations confirmed us these variable width disturbance characteristics appear under different conditions in an unpredictable way. And we also saw that adding a safety margin to the measured threshold values and using ECC can block many VRD-induced bit flips, but it also comes with the cost of significant performance costs. So I would like to start the discussion if you don't have any questions about it. Any questions?
Yeah, I wanted to ask if they justified not doing these measurements with respect to temperature.
They did. With respect to temperature, I mean,
Okay.
if I go maybe further in the backup slides. So this is temperature. They vary the temperature across different manufactured chips here to see the effects here.
Okay.
For example.
Well, that's it. Thank you.
They did, but there are also a lot of things I wanted to talk about, like the data patterns, what the effects of the data patterns that they have here. But unfortunately, that if I talk all of them about this, we're not going to finish this in time. So I put it in the backup slides. If you have any questions, maybe we can ask from here. If I have maybe the effects of temperature in another. Maybe they just have this one. So this one considers, if we can see expected normalized value of minimum threshold with one threshold measurements for the row side data pattern. So this, they try to fix the other parameters and try to vary the temperatures across the test runs here. And we can see that the temperature does not have a single, a correlated effect. That means that if we increase the temperature, that doesn't mean that it will do worse profile across all of them. So we can see that the expected normalized value changes in between different chip types here. If you keep the stable temperature, but we can see that these expected normalized value, which is the ratio of the observed threshold value, if we did the simulations and divided by the ground truth value. So if this expected value is higher, that means that we are further away from these thresholds. So the lower is the better one. And there is no pattern that yields to the lowest one across all of them here. Any more questions? Okay, I'll start with the discussion. You saw some of the slides. Yeah, they give something away. So maybe this is something cliche, but I would like to ask the audience if we could integrate these, maybe machine learning to the proposed solution. Maybe can it accurately predict the threshold value compared to the statistical approach of the Monte Carlo construction? And before asking this again, I would like to also ask another follow-up question. So if you don't think these machine learning approaches are good, can we still play around with statistical approaches? So is it still the best shot at solving this problem? Or you believe that we can implement maybe machine learning algorithms that can maybe perform better with lower overhead as well as maybe more performance? So you guys have any idea about this? Well, in my point of view, the statistical approaches could fail under the randomness assumption that we shown here. So because this phenomenon shows really high variance as well as randomness across all the tests, the statistical approaches in that sense could not maybe improve our solution. So most of the state-of-the-art solutions really work on the statistical facts. So I believe maybe the statistical approaches aren't really very effective under the huge variance and the randomness that we shown here. As such, maybe we can also continue on machine learning. What kind of methods can we use? Can we use like decision trees from supervised learning, maybe to just to make decisions about if this threshold will fail in this time or in this memory opening, closing, or maybe just implementing unsupervised learning methods such as reinforcement learning, which we saw in hybrid storage systems as well as prefetching solutions, or maybe just implement neural networks or convolutional neural networks, which maybe they can possibly catch some patterns that our statistical approaches are not enough to catch. But in this sense, the randomness makes it difficult, and in this case of decision trees. And it requires a lot of measurements for unsupervised learning such that we may need to have millions of measurements, which is not really feasible at the current state of the profiling approaches that we have. So you guys have any, ideas how we can implement, which type of machine learning algorithms will benefit our solution? Any idea? No. So in that case, maybe we can move something that is more answerable. So if we decided to build a solution from scratch, meaning that we decide to throw all solutions or mitigations away, could we adapt similar solutions from the industry? In this case, we have Avatar, which is used as a mitigation strategy in variable retention time. So in variable retention time, maybe some of you remember, we have the problem that some cells exhibit a strong retention time. And as the time goes on, or as the parameters they change, their retention times may drop suddenly, meaning that if they can hold their charge for 64 milliseconds, they can maybe at the next iteration can only hold their charge for 32 milliseconds. So Avatar is used in this case as a mitigation strategy. So in its essence, what it does is it schedules memory scrubbing operations, which is mentioned in the previous presentation. So in each memory scrubbing operation, it skims the memory cells for any bit flips. And after it sees the bit flips, it tries to correct the bit flips. And it also assumes in its solution, because it schedules these memory scrubbing operations in a span of time such that the number of unique bits is not more than one. They assume that this is a solution. So they do, like I said, memory scrubbing operations, and then to see any bit flips. If there's a bit flips, they try to correct it. And as next, they try to mark that cell as a weak cell showing with variable retention time, meaning our system from now on will try to refresh these cells at a faster rate. So I believe there's a similarity in these problems in variable retention time as well as variable read disturbance. So we may be able to adapt this solution, I believe. And in that case, you have any ideas or maybe ask questions about this implementation, because I believe there's a similarity of these problems such that we can maybe just play around with the algorithm such that our solutions can also be implemented in our problem. So any ideas?
I guess it's challenging to answer since
I try to explain, the problem. I try to explain the problem, draw the conclusion that can be similar, but maybe just overall question is that if there's a similarity between problems, can that solution of that same problem could be adapted to another one? Maybe this is just a typical question. In most of the cases, can we just adapt a solution that is used in other problem, but the problems that we want to solve is similar. So maybe we can just take this problem and implement in our system. So maybe just an overall idea. Can we just take the industry solutions? Is it feasible to implement it?
Maybe you can go point by point, what you find similar and
like I explained, the similarity is that there's a variance problem in both of them, meaning that in one problem we talk about the retention time. That's a cell's retention time is for how long it can hold its charge without any refreshes. So in this case, we also have the raw problem. Like before any medications, there's also some threshold we have. So if we go across those thresholds, we will probably experience a RowHammer attack. And both of these, show some variance characteristics. And the mitigation strategy used in the Avatar also assumes that we are also going to encounter just a single unique bit flips between each memory scrubbing operation. So a system maintenance schedule.
Can you see any obvious reasons that this wouldn't work? For example, like some huge differences in the two approaches?
Well, I believe in that in the Avatar's case, the assumption maybe could fail because it schedules these operations such that it also it assumes that there will be at most one unique bit flip, and which means that in our case we also try to show that if we just implement a margin we larger than 10%, we'll also have a single unique bit in our system, which is, the assumptions are similar in this case. And there's also a problem of variance, meaning that a cell can show a strong characteristic, may fail over time and show weak characteristics, which is a similar problem here. Because of these thresholds change over time, if we show a high threshold value, which we can say a strong characteristics, it can drop over time and show maybe weak characteristics. So which if we discussed, and we can say that these problems are similar in a sense. Maybe I'll try to ask more easier questions actually. So instead of calculating these thresholds separately, can we calculate these in batches? Like instead of calculating each of these threshold values for each row separately, can we calculate in batches, meaning that according to some neighbor like distance metric, we select some number of maybe 10 rows that we want to have in a batch, and then we just measure one of the threshold of just single one, and then assign similar values to them, or maybe assign similar variance metrics to them, even though maybe not the threshold values, but maybe say they will exhibit similar variation characteristics, so we can just assign similar characteristics to them. I mean, the problem only here is that these spatial behaviors are debunked, meaning that two rows that are near to each other in a DRAM row would likely not exhibit the same threshold values. So the spatial behaviors were debunked in that sense, but maybe the variance characteristics could be still same. So if that's the case, in that case, could we maybe just calculate these thresholds in batches, or maybe take some assumptions about this, still within the presence of the randomness and the uncorrelations? So could you think we can calculate them in groups, or just we have to do it single calculations for each threshold value? I mean, what would be the risk of assigning maybe similar characteristics without actually profiling them, see the characteristics of some rows in a batch? If not, anyway, if there's no question, I'll go further. I would like to also discuss this question, but since nobody has answered the avatar solution, it will likely lead to a similar discussion, me discussing only with myself. So I'll skip this and go to a really easy one. So we saw that these, also want to ask, so should manufacturers start to also measure the variable with disturbance metrics during this test production to assess quality of the chips? So we saw by now that manufacturers have started to measure some of the disturbance thresholds aftermath of the RowHammer and row press attacks. They wanted to measure the quality according to those attacks, and they started to, in that case, should we also do the same for the variable with disturbance metrics? So here I have two chips, one exhibiting low threshold and a low variance characteristics, and on the chip we have a chip B which has a high threshold value but also exhibits a high variance. So which would you consider more reliable? So which metric is for you the important? Does the variance is important in reliability, or having a higher threshold is more important metric for you? I mean, there's no wrong or right answers in this case. It all depends on your idea. So,
well, I assume that we would benefit more from low variance, as that would make the chip more predictable. And in terms of whether manufacturers should start doing more measurements. I doubt that that would be feasible, as that would surely increase costs a lot with measurement that seems to be based on randomness to this extent.
So would you consider a variance a better, more reliable metric than the threshold value that was maybe advertised in the chip? So in that case, I assume that you say you like to assume that variance is a more important metric than threshold, right?
Well, I feel that the variance definitely helps more, I think, as it's, or well, I just think that.
Well, low variance helps with the current assumptions, because the current all mitigation strategies, like I said, assumes that these thresholds values are the same. So in the case of the low variance, the current mitigation strategies may work better. That's the case, yeah, in that sense. So in my opinion, the variance is a more important metric right now, because like we saw, the current mitigation strategies would work on a low variance chip. So in the chip B, in that case, even though it has a high threshold, it's likely to fail under the current assumptions that the current mitigation strategies that make. And lastly, would you trust the manufacturer's measured metrics in that sense? And could you be able to replicate those measurements themselves? So in that case, the problem is that you may not be able to confirm these variance or threshold metrics by the current profiling techniques that we have, because we saw that it takes a lot of time to just profile a single bank. And at this case, we may not be able to maybe just confirm these metrics, such as we may not be able to reach the advertised threshold value at all, because we assume that this threshold value changes over time. They can just say, we have this lowest threshold that we encountered, and maybe you would try to test it at home and you will never reach that value because it's just maybe guard banded by some value. In that case, maybe any comments on that? Would you like to do it yourself, or would you trust the manufacturer? In that case, yeah, that's all. Thank you for listening, and thanks. Yeah, I would like to thank Giray for his mentorship during the preparation as well. So if you have any more questions, we also have some backup slides.
I think this was a good presentation. Unfortunately, there was so much discussion. I think
yeah, it's people have to come prepared, and this is unfortunately not something I can control. But yeah, maybe the questions I would like to ask more questions, maybe easier questions then. But the discussion will be like a kindergarten discussion, like talking about basic facts. That would be the hard. So maybe I could have recommended that people maybe come look at this paper before coming. But this is unfortunately
also possible. It was maybe a bit difficult to also discuss, right?
Yeah.
I think your weaknesses were on point, and it highlights a different way of solving this problem, right, is needed than what we kind of propose in the paper.
Yeah, because there's still a probability, like the previous solutions have also some probability assumption that some probability that could fail to mitigate some multiple bit flips. In this case, it's also shown because even we do maybe if we how was it so there are still multiple bit flips. Maybe how much should I go back here? So this is just by implementing safety margin of 10%. We see there are at most 5 unique bit flips. And for the margins larger than 10%, they said that there isn't any more than 10 bit flips. But we cannot fully confirm this, like I said, because it considers some limited environmental values as well as maybe some limited test permutations that they constructed. So in the future, maybe there will be much more parameters that we need to consider when implementing such solutions. So in that case, it's not different from the previous approaches. So it's like a fix, it's like a temporal patch to the current one.
I was referring to the, the online profiling thing. You made a good point about that. And maybe a distinction there is when you do online profiling instead of maybe offline, one-time profiling, you can distribute the overhead of performing those testing, that testing over time, over maybe the the runtime of the whole system, I would say, right? And that helps a bit reduce the overhead, but you still have to deal with the tail distribution that you need to catch before you release this product. And it's like a cat and mouse game that will never basically end. And I guess you showed some, maybe you didn't show them completely. It was in your backup slides. We evaluate the amount of time that people need to spend testing, on testing, if they want to develop a very comprehensive profile like we did. And it's like, it's measured in years sometimes, which is not going to happen.
I said if you want to profile a single bank just of 265,000, it takes like 39 minutes. But if you scale up to the whole chip, maybe maybe years.
And also multiple times, right?
Yeah.
So what you really want is a way to predict. I think you were going there with the machine learning suggestion as well.
Yeah.
Predict the variance across chips. By relying on data from only a few chips, which is something I think yet to be shown by research. So this is very fresh, right? It was presented just 2 months ago. So there's a lot more to do. And I think one of the discussion points you mentioned is, was it about spatial correlation in this, right? I think that's one of the experiments someone interested, like some person who's interested in doing that could just perform in our lab. It's not just, this is open source, it's reproducible. We have, a lot of machines, and we love to work with motivated students who want to develop the state of the art. And I talk too much, and do you want to add some stuff? I want to keep people here for much longer.
What happened to this thing? Okay. Yeah, I think I don't want to keep people also, but it was a very good presentation. I wish we had more discussion. Like everybody else, but hopefully next time there will be more discussion.
Asking something in the Moodle chat, or if they want to.
Yeah, but I think this is a very fresh paper, as was discussed, and this is, in my opinion, like discovery of issues that no one has ever talked about before, and that's a very good thing. So in the end, we're doing a lot of engineering, but we're also doing a lot of science. So by understanding how these devices behave as they scale into the future, and uncovering what lurks inside them that no one has really talked about, is very interesting and very cool, in the sense that I think there will be people, hopefully, who will develop some device level understanding of this. Right now, there are no papers on this topic, which is quite interesting, I think. I'll leave it at that. And definitely, as Atabak mentioned, if people are interested in doing research in these areas, you should definitely contact us, because this is the cutting edge. This was published 1 month ago. You cannot get more cutting edge than this unless you're exposed to something that's internal, that's not published. All right, I think we're done. Are we done? Yes. Okay.
People for here to the evaluation forms on Moodle. I have sent you an email about it. Sorry?